So hello everyone, how are you guys doing? First of all, let me welcome you all to the Unacademy JEE English. This, as you know, is a brand new channel by Unacademy where everything has been taught to you completely in English. So this is the series that I host for class 12 students, and the topic that we are going to discuss today is electromagnetic induction, and this is lecture number 4. Today we'll be talking about statically induced EMF. Okay, so before we get started with today's lecture, let me introduce myself for those of you who don't know me. Uh, So this is my introduction. My name is Rohit Dixit. I studied mechanical engineering from IIT Delhi, and for almost past 8 years, I've been teaching physics for the IIT JEE exam. All this teaching so far has been offline, and this is the first time that I'm teaching online on this Unacademy JEE platform. I myself was All India rank 47 and of 192 in the two stages of the IIT JEE exam that I took as a student. Now, I also qualified the NTC stage 2 and I was in the top 1% in the NSEP. I've already coached many students to top ranks in the IIT JEE exams, so both mains and advanced. Now, I hope to continue doing that here with you guys online. All right, so how can you guys ensure that you are not missing out on your education? Good evening, Mr. Rajesh. How are you? And your preparation goes uninterrupted. So this is how you can do it. Get yourselves the Unacademy subscription. With this subscription, you will get benefits like live classes, get to interact with the educators. Then you have live polls and leaderboards. You also have test series and analysis sessions. And finally, you have live doubt clearing sessions. So with all these benefits, trust me, your preparation will definitely keep on going uninterrupted. Then, on top of all these benefits, Unacademy also provides you the opportunity to study from the best teachers all across India from the comfort and safety of your home. So, what are you waiting for? Go out there, get yourselves the subscription. And these are the courses that you will get that you can register on the Unacademy Plus if you want. Okay, so there are three courses which are being hosted by the JEE English team for JEE Advanced 2022 students. So these are three courses, advanced level courses for class 11 students that you can enroll in. So these are detailed course on graph sets and relations and functions by Abhinav sir, advanced course on redox and equivalent concept by Rahul sir, and advanced course on mechanics by myself. Okay, then you have four more courses for JEE Mains and Advanced 2021 or class 12 topics. So here also I am taking a course which is an advanced course on electromagnetism. Then Abhinav sir is taking a course which is a complete course on differential calculus. Then there's a course by Rahul sir, which is advanced course on chemical kinetics. And finally, you have a course from Murli sir, which is a detailed course on optics. Okay. Now, how do you get the subscription and how do you enroll in these courses? Very simple. First, you'll need to install the Unacademy app. Once you have done that, you will go to the plus section of your app. Now, select your goal as IIT JEE and click on that get subscription button. Okay. So when you are redirected on the payment page, here you will have room which will say, do you have a code? That is where you can use this code, RD Live. This is my code. You can use this code to get another 10% off on already a very competitive fees. All right. If you go to any reputed offline setup, then you will realize that the fees that they charge is anywhere between 4 to 8 times this. Okay. So trust me, Unacademy is providing you the same quality education from the similar top quality educators at a very competitive price, which again, after using this code, will become even more attractive. So use code to get 10% off flat across all these fees. Okay. Now you will also know that realize that no cost EMI is available for 6 month and above subscription plans. If you're going for those, then you can also avail yourselves the no cost EMI options, which will definitely never let you feel that burden. And that is it. Then all you need to do is click on proceed to pay. All right. This is how you get yourself the subscription. Finally, if you guys are following us on the JEE English channel of YouTube, then you can connect with us on the Telegram app using this link so that you're not missing out on any of the lectures or schedules that are being announced or posted on the JEE English channel of YouTube. Okay. All right, then without any delay, let's get started with today's topic of discussion. And today we'll be discussing about electromagnetic induction. Okay. So this is lecture number 4, and we will continue our discussion about statically induced EMF. So we realized in the last class that statically induced EMF was nothing but the EMF which is induced when the flux linked to a coil starts changing because of a time varying magnetic field. Okay. And to explain this behavior, we brought the concept of electric field which gets induced by a time varying magnetic field. So we discussed this, that any time varying magnetic field induces some circular electric field lines. So these field lines form closed loops. Okay, they are always in circles. They are non-conservative in nature. Okay, they form closed loops. They still have this F equals QE, which is valid for these fields. However, the concept of potential has no meaning. Why? Because this is a non-conservative field. So potential we know is defined only for conservative field. So this is a non-conservative field. That is why we don't talk about potential due to this. Now, induced EMF due to this field between these any 2 points would have depended on the path. So for instance, let's take up on this example. So you realize in any of the circuits, the EMF is getting induced because of these field lines. Okay, so let's take some example of the induced EMFs. Okay, so how are the EMFs getting induced in different situations? So maybe let's just add a page to discuss that. Okay, so where are we here? Let's add a page there. Okay, so, yes. So let's think about it. Think about how the EMFs are getting induced. Okay, so give ourselves shapes to draw. So let's assume that this was a circular loop. This was a circular loop which is placed in a magnetic field, and the magnetic field that goes. So let's give this guy some color. So imagine this was a magnetic. This was a contacting loop placed in a magnetic field, which is something like this. Okay, so imagine this, and imagine that this field is varying. Now, if this field was varying, then you realize, according to Lenz's law, the induced EMF tries to oppose the creation of flux. So suppose that this is the field which is going down. If the field was increasing, then the loop would try and oppose the increase in the flux which is passing through into the plane of the paper. So to uh, negate that, the current in the loop would be such that it would create an outward coming flux. Okay. So you will realize the current in the loop would take up a direction which would be like this. Okay. So this is the kind of current that you should have seen in the loop. Now, why is this current flowing? So here, what I will tell you is that in the entire region, even if a conductor is there or even if a conductor is not there, what you will see is you will see some circular electric field lines getting induced. Okay, so let's try and see how that is happening. Imagine that there is this, and let's draw ourselves a smaller circle. So that is what is happening in the entire region. You will have such circular electric field lines being induced. Okay, like this. Okay, imagine that. So that is what is happening. You are getting these red lines. These red lines depict circular electric field lines. Okay, so we'll have such electric field lines which are getting concentric circular field lines are getting developed all around in the complete region of this magnetic field. Okay. So now that is what it's doing. That is what is making this current flow. Okay, you will realize here also inside this conductor, you will have these electric field lines which are continuously pushing the charges in the loop and causing the current flow. Okay, So I hope you can see that this is how the EMF is getting induced due to these circular field lines that are getting induced. Now suppose let's take up another shape. Okay, so let's imagine if you had let's imagine if you had a rectangular loop, then how can I explain? Or a square loop. So imagine a square loop. Okay, and imagine that this is also kept in a uniform magnetic field. Okay, so yeah, this was the loop kept in a magnetic field again like this. So as long as you have a magnetic field which is varying with time, see the field lines are going to get induced whether this conductor is kept there or not. Okay, that is what you need to realize. The field lines of circular nature would have gotten induced irrespective of whether this conducting loop was present in this region or not. Okay. Now we will try to see how is that electric field that is getting induced is causing a current flow in this. Okay. Let's try that. Okay. I hope you can visualize this. So try and think about it. This is what is happening. The moment in this region the magnetic field started varying, you had these circular electric field lines which started getting induced in the entire region. It's it's a lot of these things are getting induced. Okay, and let this move. Yeah, that is all right. So this is what is happening. Okay, you are getting induced. This entire region is getting filled with these circular electric field lines, which are getting induced in the entire region because of this time varying magnetic field. Okay, that is what you have to imagine. Okay, let's draw some more of these. Let's draw ourselves some. Imagine the uh, let's try and arrange these also. Some- this looks fine. Okay. All right. So this is what is happening. Okay. So you've got yourselves these concentric field lines. Okay. So okay. And slightly this is Okay. Yeah. So imagine what is happening now. Okay, so sorry that took that took a little bit of time, but I wanted to draw a picture which you guys can be clear about. So what is happening is that at every point, if you see the field lines are going like this. Okay, the field lines are going like this. So imagine what here. Here the electric field would be a tangent to this. Agreed. So what is the electric field component here going to be like? It is going to be like this. So you realize a component of this is going to be in this direction. Similarly, the electric field here is going to be like this. So a component of this is going to cause the charges inside to move here. And similarly, here the electric field will be like this. So the components of all these circular electric field lines which are lying along this direction will be the ones that will cause the current flow in this square loop. Okay, I hope that makes sense. I don't know if I am able to show you what I'm trying to show you, but let's hope. So I really hope that you have got it. So as I was saying, so here electric field would be like this, the E vector instantaneously, right? It has to be tangential to the field line, right? So these are the E field vectors, right? So they will have two components. I can divide this component and this component. So it is these components that lie along the length of the conductor that are causing the charges in the conductor to move. Okay, you realize this these components of these field lines which are along this line. Similarly, along this line, all the components along this, and here also all the components of these tangents along this. Similarly, all the components of the tangents along this. This is what is causing the current flow in this conductor. Okay. So this is how the currents are able to flow due to this circular magnetic field. Okay. Now let's try and analyze some questions related to this. So first of all, this is a very standard question, very standard situation which we are asked often to analyze. Okay, and it says the magnetic field at all points within a cylindrical region whose cross section is indicated in the figure starts to increase at a constant rate of alpha Tesla per second. Now you have to find the magnitude of the electric field that is getting induced as a function of small r. Okay. Now, the distance from the geometric center, which is, and the R can lie inside and outside both. Okay. So that is what you have to do. Okay. So try this. Let me know how you would have gone about this. Okay. Okay. So I hope you guys are trying this. You'll have to excuse me a bit because I'm still not feeling perfectly all right. Okay. So try finding the strength of the magnetic field at a different points in this at a distance r, whether it r lies inside, r may inside, or for an r which may be lying outside. R out, and this is what r in is. Okay. Asharani says, "Sir, I have not understood the concepts in kinematics. Should I read theory or practice problems?" So what is it that you're not able to understand? So let's try and first of all pinpoint your problem. No, then we can write look for a solution. Right. First, you need to tell me what exactly is it that you're not understanding. Then I will try and figure out whether the problem lies with your practice or with your theory. Okay. So let me know about that. All right, you guys doing this? By the way, remember that you have to use the Faraday's law, okay, to get this. And these induced electric field lines not only follow, they have a non-zero. So let's just add two lines here. Add two lines here. First of all, I wanted to tell you that this also follows Gauss law, by the way. Even these field lines follow or obey Gauss law. Okay, I think that's also worth mentioning. These fields also obey Gauss law. However, integral, just that closed integral, E dot dl is equal to pi d by dt, right? Unlike, right, E dot dl being zero for the field of charges, that was a conservative field. For that, this would always come out to be zero, right? For electrostatic field. So electrostatic fields are conservative and other fields are not. Okay, so Asharani says difficulty in solving MCQ. So any particular type of MCQ or all kinds of MCQ? So I think you can try and quickly revise your theory and then practice some more. I think the lack of practice is causing it. Okay, and maybe you might just want to revise a little bit of theory before you go about solving some more questions. Okay. All right. So let's try and analyze the situation that we had. Okay. So what did we have? We had a loop of let's imagine that I have a loop. This and there is magnetic field around that loop, and say the magnetic field is spread in a huge region. Uh, that this would be the region of magnetic field. This region. Oh no, the magnetic field only exists inside the circular region, right? Oh yeah. Oh yeah. So you don't have to bother about this. You don't have to bother about this. The magnetic field turns out is only in the region, a small region of that circle. Yeah. Okay. So Newton's law of cooling. Why do we write a negative sign? Because temperature is decreasing. No, temperature is decreasing with respect to time, bache. That is why you use that negative sign. Correct. The rate of cooling is, you're talking about rate of cooling. Rate of cooling would be a positive number. Okay, that is why. While dt over dt would be negative, because the temperature is decreasing with respect to time. Okay, so let's consider that I consider a segment of at a point at a distance r from the center, which is lying inside. First, let's consider point which lies inside, and let's try and analyze this first. Let's try and find out what is the electric field here. So okay, so this is at a distance r. Total is that. So can I say that at the distance r from symmetry? What all can I say from symmetry? Now this region has a circular symmetry, right? So this region has a circular symmetry. Now what I can say is that E at every point should have the same magnitude and the same direction, right? These are the two things that I can draw from symmetry. That one, E should be tangential at all points, and second, E should have the same magnitude, right? If E was here, E, here it would also be E, here also it would be E, here also it would be. Okay, I hope you can see that. Okay, at a distance R, from symmetry, what you can realize is I can conclude two things. So one, E is always tangential to the loop. Second, has the same magnitude as the same magnitude at all points of the loop. Okay, got it? These are the two things that we can immediately conclude from symmetry only. Okay, and now let's see what I can say. So now now using Faraday's law, Faraday's law, what I can say is that closed integral E dot dl would be equal to minus times by B by dt. Now, since I'm doing this integral in the clockwise direction, I'm going to do this integral in anti-clockwise direction. So outward area vector would be considered to be positive. Okay, so I can say that, and here you will realize E dot dl, the angle between dl vector and E vector at all times would be, so consider this is my dl vector. So dl vector is going to be like this, and E is also going to be like this. Here also dl is going to be like this. All right, here also dl is going to be like this. So at any point of the loop, the angle between the dl vector and E vector is going to be 0. Hi, nothing, peace. So if this is going to be 0 and E has a constant magnitude, I can write this as E times closed integral of dl. And here I would have had a minus times B dot dB by dt times A, and times another minus sign times A, which is the area of this loop, times cos of 180. Why? Because B is going inside. B is going inside, and area vector will be pointing outside. Okay. So now I can say that E times closed integral of dl would be the length of this 2 pi small r. So E times 2 pi small r would be equal to dB by dt, which was alpha. I think that has been mentioned in the question. Yes. Into this area, which is pi small r square. Okay, and cos 180, and this minus goes. Okay, so what I am getting my answer as is that this and this gets cancelled, and E turns out as alpha pi r over 2. Okay, so that is how you can see the strength of the E vector is changing. So E will become higher or stronger as I move away from the center. So the density would be increasing actually. So I should have made lesser lines inside and higher number of lines crowding it outside. Okay, that is the nature of the induced electric fields. Now, similarly, you had a second part also. Second part, it said, what about E outside? What about E at a point which lies outside this? So we haven't yet solved that. So let's add one page and see how we could have calculated that also. Okay, it's page and let's see. Now let's take that case for small r greater than capital. You would have realized that closed integral E dot dl. Now the symmetry argument would still hold, right? Because the circular symmetry still holds. So this would still be E times 2 pi r, right? And also, also I can still apply Faraday's law and I can say that closed integral E dot dl should still be minus times d phi by dt. Okay. So now what I can say is that this I can write as E into 2 pi r, and how about d phi by dt? D phi by dt would have been pi r square, because that's the only area in which magnetic field exists, into dB by dt. Agreed. So here what you see, uh, r square alpha over 2r. This is this is the E that you want to find. Now you will realize in the past one. Okay, so I did not cancel this pi. So yeah, that pi needs to go. So it will be alpha small r by 2. And here also you will get r square alpha by 2r. So you realize at r equals r, both the formulae converge. Okay. So if I wanted to see the variation of E with respect to r, then let's talk about that also. So on this axis, let's draw ourselves the field. And on this axis, let's have the r. You realize earlier it was a straight line increase, y equals mx kind of a function, and up to r equals r. This is where r equals r, and after this, it goes down hyperbolically, goes down like a rectangular hyperbola. Right. So this is the variation of E versus R that you will have, and this is alpha r by 2, alpha capital R over 2. This is where the two formulae coincided for you, and that is how the variation of E with R would have looked like. So remember, this straight line increase from the origin to the boundary of the magnetic field region, right? And then it goes down by 1 over r, okay, hyperbolically going down. Okay, I hope everybody followed this. This is important. Okay, this is often asked in your question. Try and remember this. Try and remember this. Know how to speak. So you be hyperbolic properly. Ah, let's give it one last try. Something like that. Okay, so this is what it is going to look like. Remember, this is important. Okay. All right. So sorry, I'm not feeling too well, so I'm not even feeling completely up to myself. I'm making horrible diagrams and doing everything bad. However, let's try and solve another problem. Let's try and apply this in questions and try and figure out how we will calculate the induced EMF due to the time varying magnetic fields. So here you've been told for the situation described in the figure, the magnetic field intensity changes with time as a function of 2t cube minus 4t square plus zero point 0.8 Tesla. And R2 equals to R equals 5 centimeters. Calculate the force on the electron located at P2. Okay, the problem is that here we don't know where this thing is. Okay, so I think I can help you with the figure. The figure would be certainly like this. Okay, so you draw the figure. So first you would have had a region of R, and then you would have had another region of black for this, or another one. Yeah, here it would be 2R. I think this is what they mean to ask question. Okay, so this is R, and this probably is R2, which is equal to 2R, and point P2 lies somewhere here. Okay, this is a question for you. How do you solve this? So by now you should have realized how the electric field lines are calculated. Okay, if you know that how to calculate electric field lines that are induced, then you can find this. Okay, so here is what you've been given. So how do you go about this? It is very, very simple. So inside you realize again at this position from the symmetry of the situation, you could have said that whatever the electric field lines be, electric field lines are always going to be tangential and having the same magnitude. Okay. So this always remember, that is why we take these circular lines. Circular lines, we can use the symmetry here. Now, what I can say is, okay, so to always to determine the electric field of the strength of the induced electric field, what you're going to do is you're going to say that E closed integral E dot dl, right, which is going to be E into 2 pi r. This would be equal to pi r square into dv by dt. Agreed? Because this is the rate of change of flux. Magnetism ka quiz. Okay, Harish. So maybe on the coming Tuesday we can have magnetism ka quiz. Okay. We did have two quizzes already for magnetism. One for magnetic effects of current, one for magnetic forces on charges, moving charges. Okay. So we will have another quiz probably next Tuesday or maybe I don't know. So have you taken those quizzes, Harish? So what we will do here is we already know how does B vary. We have been told varies as 2t cube minus 4t square, 2t cube minus 4t square plus zero point 0.8, is it? Yeah. Okay. So from here you will need to substitute the value of dB by dt and find E. Once you find E, then you can find the force on the electron. So let's write this as 2 pi into 2r, because that is what you knew R2 as. I haven't told you in the question. So this into, let's find out dB over dt. dB over dt is square, 60 square minus 8t. That is it. So this pi gets cancelled, one r gets cancelled. What you're getting your E as is, so your E is r over 4 times 6t square minus 8t. Okay, and now let's go back to the question. Hi Zubair. The question said that find the force on the electron located at P2, okay, at t equals 2 seconds. So at t equals 2 seconds. At t equals 2 seconds. Let's see what is the strength of E is. E would be R over 4. R, was it that mentioned? Yes. 2R was given to us as 5. So R would be 5 by 2. So this is 5 by 8 into 10 to the power minus 2. Why? Because this is given in centimeters. Always put this right unit. And at 6 equals 2, you will have 24 minus 16. Okay, so that is 8. So what is the electric field strength? 5 into 10 to the power of minus 2. That is the strength of the electric field. Okay, so Newton per Coulomb. So now force on electron. What is the force on electron going to be? Force on electron would be nothing but E times the charge of it. That is 5 into 1.6 and into, you would have had a 10 to the power minus 21. So this is what? 8 into 10 to the power of minus 21 Newton. That would have been your answer. Let's see if we have that in our options somewhere. Yes, here we go. 8 into 10 to the power minus 21 Newton. So this is going to be my answer. I hope everybody followed this. This is how you will solve these questions. Okay. Now let's take a look at some other kind of questions. So here is a slightly different question. This says that shown in the figure is a circular loop of radius small r and a resistance capital R. And a variable magnetic field of induction V equals V naught e to the power minus t is established inside the coil. Now, if the key K is closed, then calculate the electrical power developed right after closing the circuit. Okay. So you have to calculate right after closing the circuit what is the power. Okay. So try this on your own. And also tell me, where is this power coming from? Try and answer this. Where is this electrical power coming from? Who is doing the work for this electrical power to get dissipated? Okay. So some energy, obviously, when the current flows through this loop, some energy is going to get dissipated across the resistor. Now the question is, where is this energy coming from? Okay. So try this and try and let me know where do you think this energy is coming from. Okay. I hope all the options are visible to you guys. So try and answer this very quick. Okay. Till then let me try and grab some water. Feeling thirsty now. Okay. Give me 1 minute to try and get some water. Until then, you guys try this question. Okay. So did anyone of you was able to solve it? Was anyone able to solve this? Okay, so let's try and see what is happening. So what you know is that this is a circular loop which has a radius small r and a resistance capital R, right? Now a variable magnetic field is established. So what you already know is EMF. What is the EMF? And EMF. EMF would have been minus a d phi over dt. Okay, so that is obviously phi small r square times a dB over dt. Okay. Now, so dB over dt would be already minus b not e to the power minus t. So what you realize is that I would have had the answer as pi r square b naught e to the power of minus t. Okay. That is what I am getting. Let's write this. Okay. So since I know the EMF, now I'll also know the current. Okay. Let's try and write the current. Since EMF is known, I can say I would be equal to EMF over R. Okay, agreed. So once you know the EMF over R, so what you will realize is that this is pi small r square into B naught over capital R. This will be the current at t equals 0, right? At t equals 0, you realize this will become 1. Okay. So you have current as this at t equals 0. Now the power obviously would be, how much will be the power? Power would be square of this into R, right? Power, you know, P is I square times R. So let's see which option do you think is correct? I square times I square R. So I square would have meant pi square small r to the power 4, B naught square and over R. Let's see. I think, yeah. This is the option that is matching. So A would have been the correct answer. Agreed? I hope everybody followed this. Okay, here is another problem. A conducting circular loop made of thin wire has an area of cross section which is 3.5 into 10 to the power minus 3 meters square and a resistance of 10 ohm. Okay. It is placed perpendicular to a time dependent magnetic field which varies as zero point 0.4 Tesla times sine of 50 pi t. And the field in is uniform in space. So especially it is uniform, it is only varying with time. Okay. So now you have to find the net charge through the loop during the time interval of t equals 0 to time t equals 10 milliseconds. So try this problem quickly. Okay. Let's quickly try this. Sure, Lokesh. So I think I've already uploaded those notes of NLM and momentum from my end. I will need to talk to the team. Okay, I'll just need to find out from the Unacademy team why they haven't uploaded it. Okay, don't worry, don't worry. I have uploaded them on the Google Drive from my end. Okay, all right, Lokesh. So don't worry. Sure those will get uploaded on YouTube also. The links should get uploaded on YouTube very soon. Okay. All right. So anybody trying this? Or anybody trying to figure out how this is done? So what you have been told is you have to find the net charge. Okay, net charge from this interval to this interval. So I hope you how you needed to find the net charge. I hope you remember that. So okay, let's remind you. Okay, so let's remind you how to do this. Okay. So let's see what you have been told. Area of cross section is 3.5 into 10 to the power minus 3 meter square. So area of cross section has been told to me 3.5 into 10 to the power of minus 2 meter square, or minus 3, was it? Minus 3, I think. Yes, the resistance has been told to you as R is 10 ohm, right? And the magnetic field that has been told to you as zero point 0.4 sine of 50 pi t, right? Yes. P has been told to you as zero point 0.4 sine of 50 pi t. Now, I hope you remember how we used to calculate the charge. I hope you remember that we said that current would be 1 over R into EMF, which would be essentially 1 over R into d phi by dt, and this can be written as dq over dt. I hope you remember this. We had done this, so I told you delta q, the amount of charge flown, that is always equal to 1 over R times delta phi, okay, with of course a minus sign. Okay, so to calculate this, let's calculate phi initial. Phi initial would be at t equals 0. Phi initial would be 0. Phi final would have been 3.5 into 10 to the power of into. This would be zero point 0.4 times sine of 50 pi over 10 milliseconds. 10 milliseconds is 1 by 100. Okay. So Lokesh, I told you I have already uploaded it from my end like long time back. I uploaded it. I think at least around 1 month back or so. Okay, so I will see if what's the delay from the team. Okay, I will have to find out. So phi final, I realize is zero point 0.4 into 3.5. So 3.5 into 4, that would happen 14. That would be 1.4 power of. So let's substitute these values, and I would have had a delta Q as 1 over R, which is 1 over 10, to delta phi, which would have been 1.4 into 10 to the power of. Again, I'm neglecting the signs, because sign just means the direction in which the charge would have flown. Okay, so I should get 1.4 into 10 to the power minus 4 coulomb. Let's see if we have that as our options. So yes, we do. 0.14 millicoulomb. That is the answer. Okay. I hope everybody followed this. Now let's move on to another interesting problem. Okay, so this is another very interesting problem that most of the students have a tough time handling. Okay, in this question, you've been told in figure shown, the magnetic field in the region changes at a constant rate of 2 millitesla per second. You have to find the induced EMF across the ends of the rod AB. So here is a conducting rod that was placed in a circular magnetic field region. Okay, you have to find the induced EMF across this ends of the rod. So any one of you wants to try this? Give it a try. This is a very interesting problem. How do you think you will even approach this? How do you think you would have approached this? Okay, think about it. Now you will also realize that between points A and B, I had told you that the EMF would depend on the path. Okay, so I will show you from this. No, sir, you have uploaded JEE 2020 lectures, but not 2022. Okay, so let me just check it today. Okay, Lokesh, I will check it today. Okay, Lokesh. So I will let me take a look today, and I will try and upload it from my end today itself. Okay. I think I have uploaded those from my end also, but I'll still take a look. Okay. All right. So you guys trying this? Let's see how you would have calculated this. What would be the EMF induced across the ends of that rod? Let me know. No problem, Lokesh. Okay. So anybody trying this problem? No, you will realize now. Okay, what if I so one is if I want to find the EMF across AB along this straight line. Okay. So consider these three situations. One where I am trying to calculate the EMF across this straight line like this. In the second case, what happened to the width of this? This seems. So in one case, I am trying to find the EMF across this line. Another, fine, think of this. If I was trying to find the EMF across such a loop, if I had such a loop, and if I wanted to find the EMF between A and B across this, and third, I wanted to find EMF between A and B across this. So do you think the answers would be same? Do you think the answers would be the same or would they be different? So it turns out the answers would have been different, by the way. This is not your potential, not your electrostatic conservative field for which the potential would be independent of the path. Yet it would depend on the path. So turns out this would have an entirely different answer than this. And the answer to the third one would be something else only. So all three answers would have been different now. Okay, they won't be same. So how do you calculate this? Let's see. All right. So one way of calculating this was, so let me tell you. But one way of calculating this would have been that you considered a point here, okay, at a distance of small r, and spread in a thickness of some dx. Okay, found the component of the electric field. Electric field would have been perpendicular to this. Found the component of E dot dl, that would have been E dot cos theta, and then integrated that. Right, so that was one way of doing this. So one way of doing this was actually finding was integral of E dot dl from A to B. So that was method one. Would have been method one. But we will use a simpler method. This you realize would be long. Why? You had to calculate E here, E at different R's. First of all, then the angles would have been different. You would have to find cos theta. Then you would have had to integrate it. Of course, this is going to be long. How about a short method? How about a short method? So in the short method, what I will do is I will use a small trick. I will complete a triangle and form a closed loop. Because for a closed loop, I know I can apply Faraday's law. So consider a closed loop like this. So consider this was the center of the circle O. And if I close a loop connecting O and A and O and B, so this was also R, this would have also been R. Now you realize the closed integral of the EMF across this loop can be broken into three parts. Let's go through this. I can say for the triangle OAB. Okay, so let's write that for triangle OAB. Can I say that closed integral E dot dl, the closed integral E dot dl, let's write that again. So dl can be written as integral E dot dl from O to A plus integral of E dot dl from A to B plus integral of E dot dl from B to O. Okay, I hope you can see that. So once I'm going integrating along this, then integrating along this, then integrating along this. Now what you will notice is that for OA, you realize that at any point on OA, how is the direction of electric field going to be? So think about it. The electric field lines are always circular about this center, right? The electric field lines are circular about this center. So at any point on line OA, which is along the radius, this would be along the tangent. So do you agree E here would have been at an angle 90 degrees? Similarly, E here would have been at an angle 90 degrees. And you realize this would be true for any point on the line OA and line OB. Okay, that is the important thing that you need to realize. That if you realize that, then the question is solved. Now, for all points on OA and BO, would you realize this E vector is always perpendicular to the DL vector, right? So since that is the case, therefore E dot DL is always zero. Two vectors are perpendicular, then the E dot DL would be zero. Now, therefore, I can say that integral E dot DL from O to A would be equal to again integral E dot DL from B to O, and this would be zero. So now you know that cos integral E dot DL. So the entire EMF of the loop is coming only across AB. I hope you agree. The entire EMF in the loop is getting generated only across the line AB because no EMF can be generated across OA or OB. This I already know would be area of triangle OAB times dB by dt. Okay. Now, OAB is an equilateral triangle. So the area of an equilateral triangle of side R is 3 by 4 R square into dB by dt, which is 2 into power of this. So EMF across AB. EMF across AB would have been root 3R square over 2 milli. Let's see if we have that. Yes, we do. And D is the right answer. Okay, but first try this, think about this. And now once you know this trick, then you can solve a lot of complex problems like this. So this is another problem which I have seen students struggling with. So here you've been told in the figure shown that the magnetic field through the region changes at a constant rate of 2 millitesla per second. Again, find the induced EMF across the ends of the rod AB. Again, this is the rod. This lies at the edge of your circular region carrying the magnetic field. Okay, so what will be the EMF induced across the rods ends AB? So try this one. So here are your options. So again, very simple, very simple. All you need to do is remember the nature of the induced electric field lines. How were they? They were concentric circles with the center at the same point, which is the center of the magnetic field region. Agreed. Let's also this. Imagine bigger circles. Yep. Okay. It seems about right. Yeah. So imagine this. So what would happen? What would happen if I joined this to the straight line? Okay. Imagine this. Imagine this. If you join this, then what will happen? Okay, I hope you realize what I'm trying to do here. So we are trying to make ourselves a triangle. Okay, like this. Ah. Okay, so if I made this triangle, then what I will see is that triangle. Okay. Fine. Okay, very. So forget about that. So the point is what you. Okay. So yeah, what the point that I was trying to make was that if you forget about this, let's just complete a triangle. Okay, let's just complete a triangle, and what you will notice is that at any point on this line, how is the electric field line oriented? The electric field line at this point is oriented like this, so it is at 90. At this point, it is oriented like this, so it is at 90. So on radial lines, along radial lines, E dot dl would always be zero. And if you draw this, then you would have realized that this is R This is R, so this would have been 45. This would have been 45. So this entire angle would have been 90. Okay. So there are two things that you need to realize. First, very important that for all radial lines, the E dot dl would be 0. Okay, that's the first thing you need to realize. Okay, so let's make a note of that. Note for all radial lines, E dot dl would always be 0. Correct? Therefore, for the triangle shown, for the triangle shown, closed integral E dot dl, you realize closed integral E dot dl would simply be equal to integral from A to B for E dot dl. Agreed? Because two lines are radial. And this would be equal to nothing. It would have this quarter circle lying inside this. Okay, how much of flux is passing through this? That is very easy to see. And how is that easy to see? So what you can notice is that yes, this this is the part that is trapped inside this triangle. Right? It is quarter circle. Okay, what is and I use the highlighter. Alright, this is the region of magnetic field that lies inside my triangle. Okay, so I hope you can see that. What is this? This is the quarter circle. Alright. So all the magnetic flux that is changing would be the same as the change in magnetic flux through this quarter circle. And that would be easy to calculate. How much will that be? That'll be 1 by 4. This will be equal to d phi by dt. Okay, with a minus sign, of course. So you will realize cos integral E dot dl or integral E dot dl from A to B, or which I can also call EMF between A and B. That would be minus times 1 by 4 pi r square into alpha. Okay. So this is how you have gotten it. Okay. Okay. So I would either write this as from B to A or A to B. So I wrote it at A to B, so I will remove the negative sign. So this is what your answer should have been. 1 by 4 pi r square alpha. Okay. Okay, and alpha is 2. Okay. So 0.5 pi r square millivolt. That would be correct. This. Okay, similarly, another very, very challenging problem. And this is the last problem that we are going to discuss today. Okay, you've been told a uniform but time varying magnetic field is present in a cylindrical region of radius r. The magnetic field through is perpendicular and into the plane of the loop, and the magnitude is increasing at a constant rate of alpha. Okay. There is a straight infinite conducting rod placed as shown in the figure to find the EMF across the ends of this rod. Okay, so this is very, very important. So there is an infinite rod which starts at end 1 is here, the other end is at infinity. Okay, so this goes up to infinity. You have to find the EMF induced across the ends of this rod. Okay, this is a question which is a very, very similar question was asked by IIT JEE. So you need to try this. This is also a very, very tricky one. Okay. So I already told you the ways to do this. So I'll give you a couple of minutes to think of this on your own, and then I'll show you the solution. And trust me, the solution is very simple. This seems like a very tough, very complex problem if you don't know how to go about this. Okay, and let's say that this is also given to me. So it is not, and it won't even be needed. But still, let's assume that this was given. So let's assume that this is given to me as 1.5 hour. Now find the answer. So anybody trying this can write trying in the chat. All right. So you will have to excuse me. I haven't been feeling too well. Okay. So yes, that is why you will see me not being able to not only speak properly but even think properly at instant. I'm not full feeling 100% of myself. So you will have to excuse me if I seem a little off in my teaching. Okay. Let's go through the lecture and let's hope I can still make this time worth your while. All right. So how do you go about this? Okay, I think 2 minutes are up. So I told you the simplest way is whenever you have such problems. Let's write such problems, such problems. Always complete a closed loop. Problems always complete a closed loop by joining the ends of the rod to the center of the magnetic field. Always do that. Why? That'll give you two sides of your closed loop which are radial, which lie along the radius. So for them, integral E dot dl would always be zero. So here, what I will do is I will make this line. Okay, let's call this center O. Let's call this P, and then I want to join the other end with this. So to join the other end, you realize I have to draw a line which is parallel to this line, so that these two lines meet at infinity. Right? You get this? That this point will meet this point at infinity. So I can have a rectangle. I can have a rectangle which has the length which goes up to infinity. And in this region, in this entire region, the total flux that is passing through this region. Okay, that's the only region containing magnetic field. This loop. So whatever be the rate of change of magnetic field in this region, that would be the magnetic rate of change of magnetic flux for the entire loop. And for this loop, again, what I can say is that this is a triangle roughly, actually. That this point will meet this point at infinity. Okay. So for this loop, you realize about this line, the integral E dot dl would be zero. For this line, it will be zero. Only left integral E dot dl would have come across this line. Okay. So now I already know how to calculate this. That is very, very easy. So let's get ourselves that answer. For the loop shown, for the loop shown or considered closed integral E dot dl. would be equal to integral dot L from 1 to infinity. Okay, and that should be equal to minus by d by dt of this loop. And for this loop, the rate of change of flux would be the rate of change of flux through this quarter circle. From this quarter circle, it would have been 1 by 4. Again, answer would have been this. Okay, therefore, EMF in 1 and infinity, that infinite conductor would have been minus times 1 by 4 pi r square to dB over dt. And dB over dt has been told to you as alpha. So what you have is, only considering the magnitude, it doesn't matter which end is at higher potential, which end is at lower potential. So 0.25 pi r square alpha, that would have been. Okay, now let's see if that is one of my options. Yes, it is here. Okay, so let me know if you followed this. This is going to be your standard method of solving such problems. These can appear very tricky, but if you remember this trick, then they will be very easy for you. Okay, so that is it. That is where I would like to wrap up today's lecture. And I will see you next on Tuesday when we will start a discussion with self-induction and mutual induction. Hopefully, till then, I will be feeling better. And also for all you guys there, happy Diwali and keep studying hard though. And before I leave you, let me remind you that this is how you can get yourselves the Unacademy subscription. All right, so these are the steps that you need to follow. So first, install the Unacademy app. Once you've done that, go to the plus section of the app, select your goal as IIT JEE, and click on Get Subscription. All right, and when you've clicked on Get Subscription, don't forget to use this code RDLive before clicking on Proceed to Pay. This will give you a 10% additional off on all your subscriptions. All right, make sure you're using this code. And the moment you use this code, get yourselves the Unacademy subscription. You can enroll in the following courses. These are 3 courses for JEE Advanced 2022 aspirants or class 11 students, and there are 4 courses for class 12 students, which are as follows. Now, if you like today's video, then don't forget to press the like button and share it with friends as much as possible. Don't forget to press the bell icon, and the PDF notes of all the slides used in today's lectures would be available for download very soon. Okay. Now, those of you following us on the JEE English channel should be connecting with us on the Telegram app using this link. Okay, next, before I leave, one last time, let me remind you, this is my code RDLive. Okay, use this code and get yourself a next net 10% off on your next Unacademy subscription. All right, so I'll see you next on Tuesday where we will continue this discussion. Until then, you guys can take care and keep working hard. All right. Also, happy Diwali. All right, take care and bye-bye.